All right, that seems to be working. Hello, everybody, and thank you for tuning in this morning, afternoon, or whatever the time may be for you. And thank you to the organisers for granting me the opportunity to present to you all. My name is Nathan Adams, and I am a final year PhD student at Oxford, working with Matt Jarvis, Rebecca Bowler, and Boris Hausler, among a number of other people involved in the video and MITI surveys. For the next 9 or 10 minutes or so, I'm going to be talking about luminosity functions, focusing particularly on the regime where the AGN and Lima break galaxy luminosity functions are comparable in number density, in what has been called the transition regime of the luminosity function. And so coming up, I'll be introducing why this remains an area of active study. I'll then talk about a mixture of the work that I've been conducting at Redshift 4, using the video and UltraVista surveys, and I'll talk a bit about the current state of the UV luminosity function at this redshift range, before concluding with some points about where else to go in the near future. So why is it after 30 plus years of high redshift luminosity functions that we're still making these measurements? Here I highlight some of the underlying questions that remain to date regarding the general galaxy population, such as the timescales and strengths over which AGN feedback governs the shape of the luminosity function. There is also the debate over the use of the Schechter or double power law functional forms, which some studies show to be comparable in quality when fit to the data. However, both make quite drastically different predictions when it comes to the ultraluminous end of the luminosity function. Alongside which parameterization set to use, there is also the topic of parameter evolution, such as the characteristic luminosity M star or L star. Here I show some examples of studies where some show no significant evolution and other studies show otherwise. On the side of the AGN, there remains significant debate on the slope of the faint end of the AGN luminosity function, mapping the rise in AGN number counts between redshift 7 through to 3, and possibly more significant is the questioning of our understanding of our selection criteria and completeness of AGN studies. Combining all of this together, then the region of parameter space that requires additional constraints to solve these outstanding questions is highlighted with a black box on a sort of cartoon luminosity function here, where the AGN are shown in red and the galaxies in blue. As you can see, if we treat these as two distinct populations, then we are dealing with the regime where the two populations act as contaminants to one another, and this is where I've been focusing some of my work to date. And so to tackle this problem, I've been making use of the recently completed video survey. Video is a deep near-infrared survey targeting a number of popular panchromatic fields, such as XMM LSS, Chandra Deep Field South, and Alias S1, down to about a magnitude 24-ish. For the work that I'm showing today, I have focused more on XMM LSS, because this field at the time that I started doing this work was the most advanced in terms of its completion. Alongside this, I've also been using the UltraVista survey in the Cosmos field, which is a deeper survey program with the Vista telescope going down to near-infrared magnitudes of about 25. XMLSS and Cosmos have a wealth of multi-wavelength information, and so I've added optical photometry from CFHT and Hypersphere PrimeCam to the datasets to give a total of 14 photometric bands ranging in depth from magnitude 27 to 24 across 4 regions of consistent depth within these two fields. To select our Redshift 4 candidates, we decided to make use of the full multi-wavelength photometry available, and so conducted a photometric redshift fitting analysis using templates over the use of more traditional galaxy color cut. In the top right, I show our 47,000 Redshift 4 candidates in red in the GRI color space, and as you can see, a typical color cut, such as shown here with the black lines in the top left corner, while selecting a relatively pure sample, only end up picking up around about 60% of the objects, and so we are sacrificing the completeness if we were to use a simple color cut. Using around 44,000 high-quality spectroscopic objects, we find that our photometric redshifts have an outlier rate of about 4 to 5% for Cosmos and XMM LSS respectively. To manage our completeness, I conducted a simple simulation where 4 million partially resolved SAZERAC profiles were inserted into our images and re-extracted to measure the recovery rate against absolute magnitude. The plot here shows completeness for each of our 4 subfields and in 4 redshift bins of width 0.25 in redshift, between redshifts 4.5 and 3.5, where the darker colors here are redshift 4.5 going through to redshift 3.5. And so as of the end of 2018, this is roughly what the luminosity function looked like, with AGN here at the lower left corner and Lima break galaxies in the upper right corner. Just looking quickly at this, some questions can be immediately raised, examples being what is going on with the normalization at the faint end of the galaxies, where here I show 2 examples of studies where there's some minor disagreement. Alongside this, there's also a question of can we get more measurements in this transition regime to increase our confidence about what is going on with the faint end slope of the AGN. And on that topic of the faint slope AGN, there's also the question of what is the faint end slope? Is it steep, as has been suggested in the recent past by Stevens, or is it relatively flat compared to what has been suggested by Akiyama, with power law slopes ranging from minus 1.3 to minus 2. Adding the data points from our study onto this provides the following. It's immediately apparent the benefit of having both a deep and wide data set, which opens up such a large dynamical range of the luminosity function to be studied simultaneously. Re-examining the 3 points that I made earlier, we observe a normalization that is on the high end, agreeing very well with the observations from Bowens et al. In the transition regime, we find something that is a little different to what has been observed in the recent past, raising some more questions than it's probably answering, but this is something I'll come back to in just a minute. With the AGN, we measure a faint end slope that is steep, like that of Stevens, with a slope of about minus 1.7 to minus 2.1, depending which functional form we use, a Schechter function or a double power law. Our results suggest that the UV absolute magnitude is around about minus 23. AGN could still be a dominant contributor to the number counts. Now, the final point that I want to make returns us to this transition regime. Examining the methods that we used compared to those used by Stevens, I noticed a difference in how MEV was calculated in the first place. I used the best fit SED to our 14 photometric points and convolved that with a 100 angstrom top hat at 1500 angstroms in the rest frame for our best fit SED for each object. While Stevens simply used the measured I-band magnitude, which does contain the rest frame 1500 angstroms at redshift 4. If I switch how our MEVs are calculated to the method used by Stevens, I then obtain a transition regime which is more closely matched to theirs, with the empty red data points shown in this plot here. And at either extreme off the end of this plot, going into the main AGN luminosity function and galaxy luminosity function, they end up converging back into the same thing again. I believe that the use of the SED fits is the better way to go about things. The reason being is that just using the I-band magnitude alone lends itself to biases that are dependent on the redshift of the object and the UV slope of the object, while the SED fits from the photometric redshift process make use of the information surrounding the I-band to inform on the SED slopes for each individual object. So I think this is the better way to go about things, but this is something that I was chatting about on Slack and things like that if people are interested. I'll leave up a summary slide here and just say that there is still much that can be done right now, such as expanding this analysis to cover the whole of video and to push the redshift beyond 4 closer to reionization epoch. There is also the likes of the LSST deep drilling fields coming up in the near future, which will allow for future expansion of this work over the next decade. Thank you very much.